Welcome to 9-1 through 9-3. We're doing a quick introduction into radicals before we move on to chapter 10. So radicals, also known as square root sign, or square roots. If I say rad 36, I mean radical 36, which means the square root of 36. So to talk about what these actually are, if I have an x of, for example, -6, then that means I'm taking -6 squared. Remember, a negative times a negative is always a positive, so that's going to give me 36. Got interrupted there, so as I was saying, -6 squared is -6 times -6, which gives us a positive 36. Therefore, the square root of 36 is kind of, and I'm going to stretch this, positive 6 or -6. Or I can say positive 6 and -6, and we'll talk a little bit more about that later. So as I continue, -5 squared equals 25. So the square root of 25 is plus or minus 5. So as I continue through here, I'm going to do this silently and then speed it up, and you can pause at the end to copy it all down. Okay, so we have on this list, on this table, if you just look at 0 to 15, that's our first 15 perfect squares. The reason we call those perfect squares is because if we take this, well, when we square a number, we get that. So if we multiply 2 by itself, we get 4, so on and so forth. What that also means is the square root of that number gives us a whole number. And that's important for what we're getting into today, which is called simplifying square roots. So when I look over to my side over here, I'm going to use our calculator to determine if these things are true. So there's a few things that you need to know on the calculator. If I square something, that button is right here, x squared. So to square root, I'm going to take the second key, push the second key, and then push that x squared button. So if I put square root of 5, I need to close that parentheses and do square root of 20. It's very important that you close the parentheses wherever the square root sign ends. So that's important. Then I get 10. Now, if I try to do this separately and I do square root of 5, I'm not going to get a whole number. If I do the square root of 20, I'm not going to get a whole number. So it's when these two things are multiplied that I get a whole number. So the square root of 5 times the square root of 20 is 10. Square root of 100, close my parentheses, is also 10. So this particular statement, we're trying to figure out if these statements are true or false, is true. On the next one, I could use my calculator, the square root of 9 plus 16. I'm not going to, though. I'm going to just do the math. Square root of 9 plus 16, if I do 9 plus 16, just according to my order of operations, I have the square root of 25. We know the square root of 25 because over on our list here, square root of 25 equals 5. So that side is 5. On the other side, if I take the square root of 9, that gives me 3. If I take the square root of 16, that gives me 4. So I have 7. 5 does not equal 7, so I'm going to put a slash through that and say that is false. Same thing here. If I do the square root of 1, I get 1. If I do the square root of 25, I get 5. So what I'm going to do here in the calculator, and I can do this both ways. If I do the square root of 1, I should actually put in the 1. 1, close my parentheses, divided by the square root of 25, close my parentheses, I get 0.2. If I do the square root of 1 divided by 25, and that's what I have here, I also get 0.2. So I can write that as 1/5 or 0.2, but 1/5 does equal 0.2. And if you're not sure about that, you want to see that 1 divided by 5 is 0.2. That is a true statement. Square root of 36 is 6, minus the square root of 64, which is 8. That gives me -2. Now something strange happens over here. If I take the square root of 36 minus 64, that gives me a -28. If I try to take the square root of a negative number, I get an error saying this is a non-real answer. In terms of the non-real answer, you'll get that addressed in Algebra 3-4, but for now, we're saying you cannot take the square root of a negative number. And that should make sense because if I do, for example, 4 times 4, that gives me 16. Oh, I should look at the wrong one. So 4 times 4 gives me 16. I also know that -4 times -4 gives me a positive 16. So in order to multiply together to give me a negative, one has to be positive and one has to be a negative, which means it's not something squared. It's just, you can't, for the purposes of Algebra 1-2, you can't do it. So I get a non-real answer here. -2 does not equal a non-real answer, so this is false. Down here, 32 and 2 do not have perfect square answers, so I'm going to do square root of 32, close my parentheses, square root of 2, close my parentheses, and I get 8. If I have the square root of 32 times 2, that gives me the square root of 64, which equals 8, and 8 does, in fact, equal 8. So that is true. I can also check that with the calculator and do the square root of 32 times 2, also getting 8. So over here, I can do this a couple different ways. I can do 144 divided by 16, and I get 9. So this, simplified, is the square root of 9, which we know is 3. And I know the square root of 144 from my table is 12. Square root of 16 is 4. And 12 divided by 4 is also 3. So this one is true. Could have also just plugged that into the calculator. What I'm looking for here are some trends. If I look through what is true and what is false, the ones that are coming up false are the ones where I'm adding or subtracting. So when I'm square rooting, I can't just basically distribute the square root sign the same way that I can when I'm multiplying. So in terms of adding or subtracting within the square root sign or the radical, I can't do it. But if I'm multiplying, 5 times 20 equals 100. That one was true. Square root of 1 over square root of 25 was the same as square root of 1 over 25. That one was true. 32 times 2, 32 times 2, those worked out. So if I have the square root of a times the square root of b, that is the square root of a times b, or this can also be written as the square root of AB. Square root of A over the square root of B is the square root of A over B. Now, there's two ways that I look at this because I can use it this way and go backwards, or use it this way and go forwards. So there's two different ways to go about it. Okay, so I'm using this idea, the square root of A times B is the same as the square root of A times the square root of B, to rewrite or simplify my square roots. And when I say simplifying, that means I need to get as much out of the square root symbol as possible. So if I just factor 48, I have 1 and 48, 2 and 24, 3 and 16, 4 and 12, not divisible by 5, and then I'm at 6 at 8. So what I'm looking for here are two numbers that have, and I'm not going to really do this part because I'm going to use it this way. And really say that as simplify the square root of 48. So if I look at my factors of 48, this pair right here contains a perfect square, and this one right here contains a perfect square because 16 and 4 are both perfect squares. So I could rewrite this as the square root of 16 times the square root of 3. And the only reason I wrote them in that order with the 16 in front of the 3 is because the 16 is the one that can get out of the square root sign. So if I simplify that, if you think about the square root sign as jail, you got to be perfect, and this is a stretched metaphor, but you got to be perfect to get out of jail. So if you're not perfect, if I take the square root of 3, I have a really nasty decimal. So it can't get out. It has to stay put, and I can't factor it to anything that does have a perfect square root because it has no other factors than 1 and 3. But 16 does have a perfect square root of 4. So I can get that out of the square root sign, leave that square root of 3 in there, and if I put this in the calculator to check it, then I put the square root of 48, give me a nasty decimal there, or I can do square root of 4, I can do 4 square root of 3, and I get exactly the same thing. So I know that I have simplified this correctly because when I check it with my calculator, I'm getting exactly the same thing. Now, if I use the other one, the square root of 4 and the 12, I can do that, but square root of 4 gets out of the square root sign as a 2. The problem with that is that 12 also has some factors. So if I factor 12, I've got 1 and 12, 2 and 6, 3 and 4. And that one has a perfect square root right there. So I could rewrite this as 2 from there, square root of 4, square root of 3. And then I do 2. The 4 can get out, times 2. 3 is still stuck in there, which, if I multiply these, 2 times 2, I get 4, square root of 3. So if I switch over to the back side, I'm going to do a couple here. Let's try the 40. So if I factor 40, I got 1 and 40, 2 and 20, not divisible by 3, 4 and 10, 5 and 8, not divisible by 9, and then I'm back to, not divisible by 6 or 7, then I'm back to 8 and 5. So the only one here that has a perfect square root is the 4 and 10. So I would rewrite this as the square root of 4 times the square root of 10. Square root of 4 is 2. 10 doesn't have a perfect square root, and its only other factors are 5 and 2, which also don't have perfect square roots, so I'm going to leave that as the square root of 10. And that is my answer. If I look at something like number 16, 100 divided by 9 does not come out as a whole number, so I'm not going to try to simplify what's under the square root sign. But I do know that I can make that into the square root of 100 divided by the square root of 9. Square root of 100 is 10. Square root of 9 is 3. I know that's not going to come out to a nice whole number, so I'm going to leave it as a fraction. And in some of these cases, you can simplify under the square root sign, or you can split it and simplify and see what can divide out. So that is simplifying in a nutshell and why it works. So hopefully that was helpful to you. And have a good day.